The tiny island nation of Vanuatu, located in the Pacific Ocean. This is Ambrin, one of the world's most active volcanoes. Explorer Jeff Mackley climbs into the half-mile-wide crater above a seething lake of molten rock.
Well, we're hanging on the side of a cliff that's about a mile high, and just down below us is a furiously boiling lava lake, and it's incredible. Words cannot describe how amazing this is. The noise is unbelievable. The heat, there's just waves of heat that you can feel even from here. Amazing.
Heat rising from the depths of the Earth reaches almost 2,000 degrees Fahrenheit, hot enough to turn solid rock into liquid magma.
The energy required to boil rock and throw it through the air like water, Mother Nature, it's the ultimate show.
But what exactly triggers these eruptions? The answer lies several miles below the surface, in the magma chamber, a vast reservoir of partially molten rock. Magma contains gases at very high pressures. As it rises up into the chamber, the pressure builds. When the pressure gets too great, magma pushes through the rock and explodes through the surface, causing an eruption capable of throwing magma thousands of feet into the air. In the past 2 centuries, there have been over 200,000 deaths from violent eruptions around the globe, and many thousands of injuries. Including the 2010 eruption of Mount Merapi in Indonesia, which killed more than 200 people and forced 100,000 more to flee. With so much at stake, can scientists predict when these eruptions will occur and how big they will be? It's not only lives that are in danger. National economies face crippling losses. Iceland, April 2010. A volcano called Eyjafjallajökull throws a giant ash cloud 30,000 feet up and over 2,000 miles away, covering large parts of Europe. Scientists here see this one coming, but its size and impact takes them completely by surprise. A few months before the eruption, scientist Sigrun Hreinsdottir installs a new generation of sensors around Eyjafjallajökull.
It's not the nicest road in Iceland.
She tracks the sensor's position using satellite GPS. They're so sensitive, they can measure a change in position to within 1/8 of an inch. She wants to see how magma moves underground. If she can detect it moving towards the surface, it could indicate an eruption is on the way. But the magma is thousands of feet down. She can't see it directly, so she measures the way a point on the ground travels. If magma starts to move, it causes the ground above it to move too. The idea is that if magma moves into a volcano, it will push the ground outwards, which the GPS sensors will be able to pick up.
We installed the station and first we didn't see much, but it started showing odd behavior. It started moving up and down and north and south, like centimeters a day, which is very unusual. And this behavior, I thought the station must be unstable.
By the beginning of March 2010, all the GPS stations move away from the center of the volcano. Dr. Hrein realizes that the movement must be caused by a large amount of magma moving up through the Earth's crust, pushing the ground sideways. On March 4th, she becomes concerned an eruption is on the way.
I got nervous. I have to say we got nervous. We had a meeting with the authorities of Iceland and they raised the alert level.
Then, on March 20th, 2010, the volcano erupts. It starts out as a beautiful but harmless event. But over the next 3 weeks, that changes. It erupts more explosive magma, which mixes with ice on top of the volcano, creating huge clouds of ash. Video captures lightning discharging from inside the cloud, the result of ash particles creating electric sparks. The cloud rises 30,000 feet into the sky. Ash spews into the air at a rate of 200 tons per second, carried by the wind right across the heart of Europe, at the same altitude used by commercial airliners. Volcanic ash can destroy aircraft engines. For more than a week, air traffic across Europe is brought to a near standstill. The United States is cut off from most of Europe. Thousands of transatlantic travelers are left stranded. This isolated spot in the North Atlantic, hundreds of miles from Europe or the US, causes the worst airline disruption since 9/11. The total cost is over $2 billion. GPS technology allowed Dr. Hrein to observe the volcano waking up. But it couldn't tell her how big the eruption was going to be.
I really got a shock when I realized what this volcano had done. I thought it would be a little boop, and then we would enjoy the data, but there were surprises at each corner.
This is one of the challenges facing scientists. Every volcano is unique, and different techniques are needed to unlock their secrets. And there are some places where understanding a volcano's behavior is more urgent than ever. Yellowstone National Park, Wyoming. This magical place is a major tourist attraction. Home to strange colored pools and otherworldly rock formations. And geysers like Old Faithful, which regularly spits 200-degree water over 100 feet into the air. But the beauty masks a powerful force that could threaten life across the planet. Yellowstone is a supervolcano.
Yellowstone is one of the world's largest active volcanoes. Most people, when they visit Yellowstone, don't realize that because there's not the steep peak associated with most volcanoes. But behind me here, you have some of the evidence for the active volcanism of Yellowstone.
One of the greatest mysteries surrounding the Yellowstone supervolcano is its location. The Earth's surface is made up of giant plates of rock called tectonic plates. Most of the world's volcanoes lie on the edges or between these plates, where it's easier for magma to form and reach the surface. The most active edges are the ones surrounding the Pacific Ocean. This is the Ring of Fire. It includes some of the most populated countries on Earth, including Indonesia, Japan, and the USA. More than half of the world's active volcanoes are on the Ring of Fire. But Yellowstone is different. It isn't on the edge of a plate. It's in the middle of one, the North American plate. How can there be a volcano here, so far from a plate boundary? We know from looking at the rocks of Yellowstone that the volcano has been active for a long time. 2 million years ago, Yellowstone produces one of the largest eruptions ever seen on the face of the Earth. It blasts away the peaks we normally associate with volcanoes and leaves this strange, flattened landscape. Yellowstone hasn't had a major eruption on this cataclysmic scale for over 640,000 years. But the hot springs and geysers are signs that there's a lot of heat under the surface. This volcano is very much alive, and it is intensely monitored. Here, seismometers are vital. Bob Smith is the scientist in charge.
I'm opening the lid. This is going to fall down. Of a seismic vault, and inside is a seismometer which sends a signal onto a telemetry network. And that antenna is pointed to a receiver about 20 miles down on the lake. So anything that we're doing right now, it's recording right now on my computer in Salt Lake City, as are the entire seismic and GPS network.
The easiest way underground magma reaches the surface is through a channel created by fracturing the rock above it. As the rock cracks, it creates vibrations, small earthquakes that occur days or weeks before an eruption. It's these vibrations that seismometers detect. Smith is confident that the seismometers and GPS will give some kind of warning of the next eruption. But when that might happen, no one knows. At the moment, there's no major increase in activity. Yellowstone is sleeping. But scientists also use these earthquakes and GPS to reveal what's deep inside the volcano and solve the mystery of why Yellowstone is here in the middle of North America.
Well, the seismographs do two things. They record the earthquakes that are active, and then they're used to record or scan the subsurface that we can't otherwise see.
Seismic waves travel faster through cold, solid rock and slower through hot and molten rock. As seismic waves from distant earthquakes travel through underground magma reservoirs, they slow down. By measuring these waves at multiple points, it's possible to build up a three-dimensional picture of where the magma underneath Yellowstone is located.
We can reconstruct a three-dimensional picture like an MRI scan or a CAT scan by recording thousands of earthquakes into our array of seismographs.
The seismic network at Yellowstone is extensive, with over 150 seismometers spread out over 100,000 square miles. Bob Smith is able to look deeper than ever before, hundreds of miles down. And what he's discovered is striking. A huge structure of partially molten rock beneath Yellowstone. This is a mantle plume, a rising column of hot rock stretching at least 400 miles into the earth.
This is the same concept as a lava lamp. You heat up the wax in the base over a bulb, and then it slowly rises up because it's less dense. And that's the basic concept for a mantle plume.
For scientists, seeing this for the first time is a breakthrough. It solves the mystery of why the Yellowstone volcano is here. This plume is powerful enough to force its way through the middle of the North American plate and create a volcano where there wouldn't normally be one.
Are there eruptions in Yellowstone's future? Definitely. Now, will there be another catastrophic eruption? That we don't know.
A major eruption would be cataclysmic.
What it would create would be massive volumes of material. It probably goes on for days and weeks and months. And it's destroying all the surface rocks, if you wish, in its path.
Most of the western United States would be buried in thick ash deposits, capable of collapsing buildings and suffocating people. Hurricane-force flows of superheated gas and ash would blast out, covering a 2,000 square mile area. A towering column of choking ash cloud would rise 25 miles up into the atmosphere, blocking out sunlight across the planet. Temperatures would plummet, crops fail, and millions of people would die of starvation. The awesome power of such an eruption, equivalent to the force of 1,000 Hiroshima bombs every second, is impossible to defuse. All we can hope for is a warning, a chance to prepare as best we can.
There's no way to know when an eruption is occurring in the future. Could happen tomorrow, hundreds, thousands of years. We simply don't know where we are in these cycles. That's why the instruments are so critical.
As scientists keep a watchful eye on Yellowstone, on the other side of the Atlantic, there's a volcano that could pose an even greater threat. Many experts believe the place where people are most at risk from volcanoes is here, Naples in Italy. This is one of the most densely populated cities in Europe. 3 million people live here, and it lies at the foot of the most famous volcano on Earth, Vesuvius. At 4,200 feet high, Vesuvius towers over the city. It has erupted over 25 times in the last 2,000 years. The most deadly in 79 AD, when it buried the town of Pompeii, killing thousands. They had no warning, no time to run. If it were to erupt today, the effects would be devastating. Burning clouds of ash and gas called a pyroclastic flow would wipe out large parts of the city. Over 500,000 people are at direct risk. Scientists keep a very close eye on Vesuvius. They watch for any seismic signals that magma is escaping from the magma chamber. They're confident That will give them at least a few days' warning before Vesuvius erupts. And now, scientists are using a brand new technique to help them predict how large an eruption could be. Inside a volcano is a tube, the throat of the volcano. It's the structure through which magma flows in an eruption to the surface. The larger the tube, the more magma flows through it, and the bigger the eruption is likely to be. Until now, there's been no way to see inside a volcano. Not even X-rays can penetrate solid rock. But surprisingly, a solution is found in events happening thousands of light years away, in deep space. Dr. Hiroyuki Tanaka is harnessing the power of the universe. Far out in the cosmos, violent explosions of stars send out particles flying at enormous speed. They're called cosmic rays. These fly across space, and some of them hit the Earth. When these rays hit the upper atmosphere, they create a shower of invisible particles. Dr. Tanaka is interested in the ones called muons.
Muons are from everywhere, from this direction, from that direction, or from vertical or horizontal. The muons penetration is very strong, so that building, or that building are almost transparent for muon to penetrate.
Here is something powerful enough to pass right through thousands of feet of solid rock. They can even pass through whole mountains. Dr. Tanaka has a brilliant idea. Perhaps they can be used to create an image of the inside of a volcano. He builds a device that detects the naturally occurring muons. At the heart of the device is a special kind of plastic.
When the cosmic muon arrives this device emits a very faint blue light.
These blue lights are picked up by a light sensor, which converts them into an electric current that a computer can analyze. Tanaka places these muon detectors around a volcano. As the muons pass through the volcano, some are absorbed. But where the rock is less dense, more muons pass through. These muons are picked up by the detector and form an image of what's inside the volcano. By placing detectors at different points, it's possible to build a 3D image. His first target is Mount Asama. This is one of Japan's most active volcanoes, and it lies just 90 miles from Tokyo. He leaves the detectors in place for months to collect enough muons. This has never been tried before. It may not work, but if it does, it could revolutionize prediction by revealing the inner structure of a volcano. Tanaka sees the first image.
I was very, very skeptical. So in order to validate this, I tried many things. And finally, I found that it was true. Everybody was excited. So that's very, very exciting moment for me too.
The image is crude, but it reveals the structure of the volcano. The red is the dense rock of the volcano cone. In the middle is a hole, the throat of the volcano, visible for the first time. It proves the technique works and reveals the size of the throat, critical for predicting the size of an eruption. Tanaka uses these images to correctly predict information about Mount Asama's recent eruption. By measuring the size of the throat and changes in density, he's able to track the movement of the magma. In this case, he calculates how much magma will reach the surface, as well as where it's located. Tanaka's revolutionary new technique is now being tested on Mount Vesuvius. It's the first volcano outside Japan to be analyzed with muons. It could give the people of Naples warning of what Vesuvius has in store. But here in Naples, the scientists fight a battle on two fronts. Vesuvius is just the tip of the iceberg. There's a hidden danger lurking beneath the ground. And the clue is in these ruins. This is the marketplace of Sarapeo. It was built almost 2,000 years ago. But something strange has happened since then. 10 feet up the columns is a dark band where marine mollusks burrowed into the rock. These creatures live only underwater, which means this building was once submerged.
Just standing here, we have absolutely remarkable evidence of the fact that the land must have subsided into the sea and come back up out again at least once in the last 2,000 years or so.
What could be causing the ground to rise and fall? It's not just the temple. The whole region is lifting, including entire towns. And the movement is going on today. Since the 1970s, the ground has lifted up by almost 10 feet. In the port, these boat ramps were once underwater. They're now high and dry. And just outside the town is a place that reveals the cause of this movement. Here, superheated steam and sulfurous gases burst out of the ground. The evidence is clear. This entire area is one giant volcano, containing farms, villages, whole towns within it.
In our view here, there are probably at least 100,000 people in the houses that we can see, most of whom perhaps are not completely aware that they're actually living in the heart of an active volcano. Psychologically, it's quite difficult to get that message across because there's no physical evidence of any danger.
With no obvious cone, like the one at Vesuvius, the scale of the volcano is only clear from above. The entire picturesque bay is in fact a giant volcanic crater, 8 miles across. It's called Campi Flegrei. Using the movement of the ground, scientists calculate that there's a huge magma chamber under the bay. 39,000 years ago, this volcano erupts. Billowing columns of hot gas and magma spew from the magma chamber. As the chamber empties, the pressure lowers, and the ground above it sinks down. It forms a large bowl-shaped depression called a collapsed caldera, similar to the shape of Yellowstone. Eventually, the sea floods in, forming the bay we see today. It is the largest eruption Europe has seen in the last 100,000 years. If Campi Flegrei ever erupts on the same scale as the prehistoric eruption, the effect would be devastating. Pyroclastic flows would flood out, destroying everything in the vicinity. If they weren't evacuated, millions would die instantly. Ash would spread out across the whole of Europe, triggering climate change that could last for decades. Now, researchers are about to embark on a bold project to find out what's actually happening underground. Muon scanning won't work for a flat volcano like Campiflagre, so their plan is to drill right into it. The scientist in charge is Giuseppe Di Natale.
This is an old steel factory, now abandoned, and the drilling place will be just year-round.
They intend to drill a hole over 2 miles deep. They're hoping to get a sample of rock from right inside Campiflagre. The drill will curve under the bay toward the heart of the volcano. And they hope that rock samples help answer a crucial question. Is it magma causing the ground to lift up, or just gas and heated water?
One of the objectives of the deep drilling project that's about to start is that we might be able to resolve this debate about whether the fluids that have been accumulating at 3 kilometers depth are in fact magma or heated water or some other fluid.
Settling this debate is critical for predicting the risk of an eruption. If Chris Kilburn is right, and it's magma building up 2 miles underground causing the uplift, there could be a devastating eruption. Others think it's more likely that gas and heated water inflate the ground like a balloon.
Now, if that's the case, the potential for an eruption is actually quite low because all that's accumulating is water and hot gases. The alternative, that it's actually magma accumulating, suggests that the possibility of eruption is higher.
Analyzing rock samples from the volcano itself tells the people of Campiflagre whether the volcano they're living on is heading for an eruption.
This experiment will allow us not only to understand much better this kind of volcano, but also to understand how to forecast the next eruption.
This project is only just beginning, and scientists are years away from fully understanding Campiflagre. But nearby, scientists find what might be the holy grail of accurate prediction. "150 miles from Campiflagre, in the Mediterranean Sea, is Stromboli. This island is one big volcano rising from the sea. It's erupting, as it's done every day for at least 2,000 years. But without warning, the volcano can change. It can suddenly become more explosive, sending blocks of lava 5 feet across, flying through the air. For the thousands of tourists who visit the volcano each year, these explosions can be deadly. Volcanologist Alessandro Aiupa is responsible for the safety of the visitors. He knows the only way to protect them is to predict the violent explosions.
What we have been looking for is precursory signals in the hours or in the days prior to the explosion itself.
Aiupa focuses on the volcanic gas that causes these explosions. Deep underground, the magma is at such high pressure that gases actually dissolve in the molten rock. But when the magma rises, the pressure goes down and the gas is released. It's like a bottle of soda.
If you have a capped bottle of soda, you don't see any gas bubbles here because all the gases will be dissolved into the soda. And in the same time, if you think of the magma deep in the crust, all the gases will be dissolved into the magma. But as soon as you remove the cap, all the gases will be going out of your bottle. And this is more or less the same as what is happening as the magma is being decompressed as it is ascending through the crust up to the surface.
As the magma starts to rise from deep underground, it releases gases. IUPA wants to find out whether the amount of gas released by the volcano might give a warning of a larger, violent explosion. One of the gases released is the deadly sulfur dioxide. But sulfur dioxide is invisible, so how can you measure it? IUPA's answer is a new type of camera.
So what they do is that they take images of the gas plume, but they are working in the UV region.
In normal light, there's just a wisp of steam. But with the UV camera, the plume of sulfur dioxide is clearly visible in red and yellow. IUPA also measures another gas, carbon dioxide. CO2, one of the most common volcanic gases. CO2 is impossible to measure remotely because the atmosphere contains naturally occurring CO2, which interferes with the measurement. The only way to detect it is with instruments at the summit. Scientists have to climb right up to the rim of the crater. Even when the volcano is in a state of high alert. This is the device that detects CO2 and continually transmits the reading down to the control center. IUPA measures the two gases for over 5 years, looking for a change that happens before an explosive eruption. He notices a pattern.
What we have seen is that 12 of the last 14 measured explosions have all been preceded by CO2 increases.
IUPA's theory is that the normal small explosions are caused by sulfur dioxide-rich bubbles that form at low pressure. But the big, deadly explosions are caused by magma, rich in CO2 that bubbles out deeper down, at much higher pressure. When CO2 starts appearing, a dangerous event is on the way. The theory has recently been put to the test. In May 2010, the level of CO2 increases. IUPA recommends that the volcano be closed to tourists.
The volcano is an attraction, so it's a big responsibility. But on the other hand, you know that if the volcano is creating major explosions and tourists are up there, that's a dramatic event which we really want to avoid.
Just a few days later, the volcano explodes. If it hadn't been closed, visitors to the island might have been killed. For IUPA and his team, it's a triumph. Not only have they predicted when, but just as importantly, they knew how large this eruption was going to be. Could this technology be the breakthrough scientists have been waiting for?
When you close the volcano and then you have an explosion, you feel so excited because you understand what you are doing is not theoretical science, but it has such important practical implications. You maybe are saving human lives.
But different volcanoes give off different signals. Scientists don't yet know if all volcanoes emit an increase in CO2 before a large eruption. This is why they use many different techniques to predict eruptions. And nowhere is that more important than in the shadow of one volcano, here in the United States. Washington State, 50 miles south of the city of Seattle, is Mount Rainier. It dominates the landscape around it. A beautiful and seemingly peaceful mountain. But it's a potential killer. It's part of the same range as Mount St. Helens, which in 1980 exploded with huge force, killing 57 people and causing over $1 billion worth of damage. A similar-sized eruption of Mount Rainier would be far more deadly because of the much larger population around the mountain. But the biggest risk comes not from an eruption itself, but from what it unleashes. This is a lahar, one of the most dangerous hazards that volcanoes produce. It's a churning avalanche of volcanic mud, rocks, and water. In 1985, the Nevada del Ruiz volcano in Colombia erupts. Within hours, it unleashes a lahar that swallows a town of 28,000 people. Most of them are buried or swept away. It's one of the deadliest eruptions in history. Mount Rainier has more snow and ice on its summit than any other mountain in the lower 48. If this ice comes into contact with hot lava, it rapidly turns into a torrent of mud. One of the towns most in danger is Orting. 6,000 people live here at the base of Mount Rainier, and the population is expanding. It's a risk which Jody Woodcock, a public safety official for the county, is all too aware of.
What we're looking at in the city of Orting is potentially 20 to 30 feet of mud. That flowing concrete could actually travel up to 40, even 50 miles an hour and could ultimately destroy everything in its path.
And it's not just Orting that's at risk. Geologists find evidence for many lahars from Mount Rainier, going back thousands of years. The volcano produced some of the largest mud flows ever seen on the face of the earth. Some reached as far as the present-day city of Tacoma and created floods that entered the outskirts of Seattle, 60 miles away. It's been quiet since 1882. The pressure is on scientists to forecast the next eruption of Mount Rainier. Like other volcanoes, it's monitored with GPS and seismometers to warn of ground movement caused by magma flowing underground. But Steve Ingebrigtsen is searching for another way to predict eruptions, using water.
About 18 degrees here. Bob, are we going to walk around a little bit and try and find...
Normally, a mountain stream is less than 40 degrees Fahrenheit. But the water here is 70 degrees.
Well, what's interesting about this stream, which you wouldn't give a second glance to if you're hiking, you might actually take a drink out of it, is there is chemical evidence and thermal evidence of some deep volcanic fluids affecting it.
These deep volcanic fluids could be magma or volcanic gas. Scientists don't know exactly how it happens, but somehow the heart of the volcano, over 6 miles down, heats up the water near the surface.
How did this water come to be a bit warm and have these funny chemicals in it? That's something we would really like to know more about. I think that's one of the great unknowns in these systems.
Scientists hope the water gives them a clue that the volcano is waking up. At Mount St. Helens before the eruption of 1980, there are reports of the streams getting warmer and even changing color. It seems these streams are giving us a warning, but one that's been missed by scientists in the past.
Ooh, that looks like a nice place too.
To make sure it's not missed again, Steve Ingebrigtsen is installing a new kind of sensor into the streams here on Mount Rainier.
This probe will record water pressure, electrical conductivity of the water, and temperature of water for 5 to 7 years at hourly intervals with internal storage and internal power. We're calling this site Paradise, right, Bob?
Ingebrigtsen and his team install these sensors not just on Mount Rainier, but on volcanoes all along the Cascade Range. Their work is so new, they don't know what kind of warning the sensors will give them. But it could be a valuable new weapon in the battle to predict eruptions.
We definitely hope that these sorts of water features are going to tell us something about what's going on deep in the volcano.
But even if science can predict the next eruption, the people of Orting are still at risk. There's enough unstable rock on the volcano to form a lahar, even without an eruption. A rock slippage at the summit could be enough to trigger one. And if that happens, there could be little warning. The only hope is to escape to higher ground in the minutes before the lahar hits. An alarm system is installed to give them a chance.
The key to the lahar warning system are the sensors, or what we call acoustic flow monitors. There's 5 on each upper river valley. What these do is detect ground vibration.
Lahars make a very distinct kind of vibration that tells the system a mud flow is on its way.
Once the acoustic flow monitors pick up activity, the siren that you see behind me and those throughout the rest of the valley will be activated immediately.
This is the first automated lahar warning system installed anywhere in the world. But even with the alarm, it's a huge challenge to get everyone out in time.
The city of Orting has approximately 40 minutes to evacuate, so it really doesn't allow much time, and we have to be ready to act swiftly.
In the last few years, scientists have found new ways of uncovering the secrets hidden inside volcanoes. They've made great advances in accurately predicting volcanic eruptions. In some cases, they can tell not just when, but how big an eruption will be. But there are some volcanoes that are so powerful they could devastate the whole planet. For now, all we can do is hope that they stay quiet for many years to come.